닉네임 나눠주시겠어요? Okay. So let's go to our previous lecture 11. So we are now talking about the delay of a certain circuit, a simple circuit. And previous lecture, in lecture 11, we have introduced RC model. So in this RC model, we try to express our transistor with its effective resistance and effective capacitances. So if we have a certain transistor, then we introduce a resistor and capacitor, also a capacitor, and finally we also introduce another capacitor. So here we have gate capacitance, and these are related with diffusion one. So this is if we annotate them, then we can write down this way. But in this lecture, not in reality, in this lecture we just assume that they are quite similar to each other. So that's the reason why we introduce just an effective capacitance C, but in reality they can show a little difference. So please understand those differences. But anyway, after that we have thought about the scaling with respect to width or length. If width is increased by factor of k, for example, then since these capacitances are proportional to the area, so capacitance, gate capacitance and diffusion capacitance will be increased also with the same factor of k, and resistance will be reduced, so it is quite easy to understand this way. However, in the case of L, length, it's not, because length is related with only channel region, so our diffusion capacitance does not change it, and only our gate capacitance will be scaled with our length variation. So that was one thing we have studied. And after that we have considered, for example, 3-input NAND. So in the case of 3-input NAND, it's a pull-down network, can be written or drawn in this way. There is a chain of our 3 transistors, and after that please think about this one. So each of them contribute, so it's a resistance, and resistance, and of course it has capacitance, also capacitance, also capacitance. So from the viewpoint of our V out, the route toward this ground is made of a chain of RC network. Here we have a 1, 2, 3. So in order to consider the time variation of this V out, we have to solve this system. That was the last conclusion of our previous lecture. But everybody understand this is too much complicated, because we have already made a crude approximation about this transistor model. So RC model itself is not an accurate description for our transistor. We just introduce a certain approximation. Based upon that approximation, if we do very accurate calculation using this kind of RNC model, does it improve the accuracy of our entire result or not? So everybody can understand. Already we have made a simple approximation, so we don't improve the result by solving this RC network accurately. So that's the reason why we have to consider a even quicker way to estimate the delay. So anyway, let's go to example taken from our textbook. So now think about a unit inverter. So here unit inverter means that in this textbook they assume that the width of PMOS and NMOS is 2:1 ratio, and yes, so think about this one. Then let's try to calculate this propagation delay. Then what happens? So in either case of output rising or output falling case, so everything is quite equal to this R. For example, MOSFET contribute this kind of thing. And here in this example 4.4, we assume that we have one single inverter, and this is our input and this is output. However, in the output we have multiple copies of our same unit inverter. For example, this one just draws m equal to 3 case. If we have 4, then we'll have more. Then how about this one? So in terms of our intrinsic part, so not loaded one, in this case we can find out R either when it is falling down or rising up. So also we have another capacitance. So capacitance that is given by 3 times C. Why do we have 3 times C for this capacitance? So can you follow? Because here we have a P MOSFET and here we have N MOSFET, and we assume that their ratio is 2 to 1. So in both cases, this P MOSFET or N MOSFET contribute just the resistance R. It's okay. And how about the capacitance? In terms of capacitance, since P MOSFET has twice wider than N MOSFET, so it will contribute 2 times C. And N MOSFET will contribute just to C, and they are once again they are parallelly connected. So that's the reason why when sum them all, then we can have 3 times C. Please note that this is just a contribution from this intrinsic part, our inverter itself. And now think about this load part. Here we have output and here we have output. Yes, then so please wait for a while. Okay, so now we have here m copies of these inverters, and each inverter can contribute to also 3 times C, because 2 times C from P MOSFET and just C from N MOSFET. Although we have same numbers, C 3 times C and 3 times C, but please note that this 3 times C comes from gate capacitance and 3 times C here shown is originated from diffusion capacitances. So we have, once again, we have assumed that our gate capacitance and diffusion capacitances are more or less in the similar range. So we just assume the 1-to-1 ratio between them. But anyway, now think about this part. So this topmost one will provide us just 3 times C. And how about the other one? The middle one will also contribute to 3 times C. And finally, the bottom one will contribute to 3 times C. So simply speaking, if we have 3 copies, then these loads are contributing 9 times C, which can be expressed as 3C times just M. Okay, so overall, from the viewpoint of this output node, there are 3C from the inverter itself and 3MC from their loads, M copies of our load inverters. So that will be the overall capacitance connected to this output node. And how large is the resistance? The resistance is simply R, so the time constant tau can be approximated as just R times 3C plus 3MC. So you are now having the answer like this. Okay, so are you with me? Do you have any question? Then please let me know. So it means that even when we have M equal to 0 case, even when we have M equal to 0 case, let's say M equal to 0, it means that there is no load attached to its output node. Even in this case, we have propagation delay, which is given by 3 times RC. So since the inverter is the simplest logic gate we can imagine in this lecture, so yes, in this given technology, this number 3 times RC is the shortest time scale we can expect from any kind of logic gate. So we will use this number, so the time constant of unloaded inverter, as a minimum time scale or reference of a time scale. Okay, so for example, if we have a certain time t, then that will be just normalized by 3 times RC. Then we can have a certain integer number. So you know this is a second scale and this is once again second scale. Then this division will give us a unitless number or dimensionless number. So that will give us a fair comparison between different technologies. For example, let's think about this one. You are using 180 nanometer scale, or sometimes you can use 45 nanometer scale. So you are now using two different technologies. This is quite cheap and this is relatively more expensive. And what we can expect is for 180 nanometer, this product, the IC product, is quite high, and in the case of 45 nanometer, that will be much lower than that of 180. Then let's make a comparison between two circuits made from this one technology and another technology. What is your expectation? Of course, we can expect that this guy will give us much faster transition. Of course, it is not originated from um, the benefit of new design. We just change technology and their IC product is reduced. So in order to make a fair comparison from the viewpoint of a designer, not from technology guy, then we have to normalize it to technology dependent quantities. So this RC product can be well used for our normalization. Okay. So now let's go to another example, example 4.5. Here we have a driver wider than unit width. Previously, the situation we have considered was like this. Here we have a unit inverter, and here also we have a unit inverter, and another unit inverter. That was the situation. However, let's just say 1, 1, 1. Here 1 means that they are all unit sizes, and here we have previously 1. Now we are considering the case instead of this one. Now we have a factor of W for this driver. This is a driver and they are loads. So we are now working with this case. Then what is your expectation? Load is the same, however driver becomes more powerful. So what we can expect is, if we have the propagation delay comes from driver itself and load part, let's say that this is the component originated from the driver itself, and there is another component comes from driving the loads. Then if we have more powerful driver, then what we can expect is maybe this part will be reduced. Then how about this driver part? So that is our question. Then let's just consider this one. Simply speaking, if we just draw our circuit schematic, then it can be written like this. Previously, when we consider unit inverter, then we say that this is with 1 and P MOSFET as with 2. However, in this case, now we have, instead of this number 2, we have 2 times W. Are you with me? Then also in this M MOSFET, we have, instead of this just number 1, we have W. Then if we consider once again discharging phase, then what we can expect is, in this case we have 3 times C, because 2C from P MOSFET, 1C from M MOSFET. Then what is your expectation about the capacitance, diffusion capacitance? Simply that will be 3 times WC. So since we have W times wider channel, so it is quite obvious that we have a wider or higher capacitance value. However, that does not immediately mean that this driver related propagation delay is scaled by factor of W. Because, once again, if we have a wider channel, then resistance, previously it was just R. However, now it becomes, instead of R, it becomes R over W. So simply speaking, if we just calculate the product between its effective resistance and effective capacitance, then it becomes simply 3 times RC. That is an important observation.
지금 3타임즈 RC라는 게 왼쪽에 곱해도 3타임즈 RC고 오른쪽에 곱해도 3타임즈 RC인데 그러면 그 둘 중에 하나만 고렸을 때 3타임즈 RC라는 말씀이실까요?
So okay, so good question. So let me just repeat his question once again. So here we have tau equal to 3 times RC. So when we try to calculate tau propagation delay for this unit inverter, we calculate or we obtain 3 times RC. Even when we have a wider channel, even in this case, we can have tau equal to 3 times RC. So simply speaking, regardless the value of W, an inverter has propagation delay, its own delay equal to 3 times RC. So with independence is just to observe. Okay, so
그럼 두 개 합치면은 좀 달라지는 거예요?
what is your question? So he asked me, when we sum them all, is this the difference or not? However, what is the meaning of sum these two inverters?
이게 드라이버고 오른쪽에 있는 게 로드라고. 네.
Okay, so his question is now like this. Here we have 1 and W. Then what happens? So in this case, the answer is quite simple because, you know, this is just M over our previous example. So it becomes simply 3 times 1 plus W RC, because this W is acting as just number M in our example 4.4. Okay. However, that also gives us another question. Okay, that is quite interesting. Instead of this one, then how about we make it this way? Then do you expect also same thing like 3 times 1 plus W RC? Actually, it's not. I mean that the answer now becomes somewhat interesting, like 1 over W. Because, you know, from the viewpoint of our previous, our driver, in this blue case, load is W times heavier. However, sorry about this red colored one is for our blue case. And now in this new case, when driver is W and load is 1, then we can say load is just 1 over W of a driver. So it is quite light. So it simply means that if we have heavy load, then it increases the propagation delay. If we have light load, then it reduces the propagation delay. Of course, if we have this W quite large, then it is corresponding to almost unloaded situation. Okay. So is it enough for your question? Okay. Then let me just once again, although we have already disclosed the answer of this example 4.4, then let me just do it, or try to find out the answer more systematically. So up to now, we have just studied the with independence of propagation delay. However, that was all related with this driver related part. Now we have to consider this load part. Then what happens? So let's assume that in both cases we have introduced same load. So I mean that here additionally we have, oh sorry about that, let me just use different color. So we have just attached here 3MC here, and here also attached 3MC. Same load is attached to these two drivers. So simply speaking, yes, here we have a unit strength inverter. Well, after that we just added 3MC, and now we have more powerful inverter, W times powerful than the normal one or unit one, and same 3MC is attached. What is your expectation of propagation delay originated from this 3MC? Even though they are the same, but driver in this case, this one is more powerful, so it can easily charge and discharge this same capacitor. So what we can expect is tau for this part, this lower one, will be shorter than the upper one. Then let's just go to this one. The propagation delay calculated from this case can be obtained by R times 3C plus 3MC. This is exactly our previous example 4.4. Then how about this powerful case? In this case, now we have R over W. Resistance is reduced and capacitance is increased. So they give us the same product, 3 times RC, when we consider intrinsic part. However, please note that here we have 3MC. Capacitance is not scaled. However, resistance is scaled. So the answer now becomes 3 times RC from its intrinsic part, driver related part, and second part is related with 3 times RC, and additional factor becomes just M over W. Are you all with me? So simply speaking, we can say that the propagation delay has some relations like this, and this one just gives us a part intrinsic to inverter itself, and another part related with the relative strength between our driver and its load. Okay, if load is too heavy, M is large, then we can expect an increase of propagation delay. And if we have very powerful wide driver, then we can reduce the propagation delay. Okay, so this ratio M over W just to represent the ratio, strength ratio between this driver and load, and we sometimes call it as a fan out and use this expression. So if fan out is large, then we have a longer propagation delay. Okay, do you have any question? So if you have any questions, then please interrupt me. This is quite an important concept in this lecture. So simply speaking, once again, driver has certain its own contribution to tau, and load has its contribution to tau. However, this tau is not solely determined by load itself, but the relative strengths between driver and loads are important. That is the main message of this lecture today. Okay, so now let's go to this slide 8 once again. The main motivation was, let's just come back to our pull down network for 3 input NAND gate. Then yes, here we have a P out, and it can be approximated as, first of all, we have a certain cap and resistance, and another cap and another resistance, also another cap, and finally resistance, and that is grounded. So that is a simplified view of our pull down network, and we are now talking about discharging speed of this V out voltage. Then, in order to make this discharge, of course, if we don't have any kind of this intermediate capacitances, yes, then that can be well approximated or well modeled as just a series resistance of these 3 resistors and single capacitor. That can be just written as R, C, and yes, and we have the initial V out, and its behavior will be simply given by this way: V out as a function of t after sudden switching. Then we will have V out at initial value and exponentially decaying by this time constant of RC. Of course, here R means that the sum of this one, and finally this one. However, as we have discussed once again in our previous lecture, if we recover this intermediate one, this guy, that guy, this guy, and that guy, then we cannot no longer make a simple summation of this one. So that makes our life quite complicated. This slide number 8 just shows that, oh, don't worry about that. Although we cannot calculate the exact behavior of these cases, but we have some remedy for it. Was good approximation. Let's call it as R1 and C1 and R2 and C2 and finally R3 and C3. And we are now talking about the discharging speed of this one. So it is important. We are not talking about the discharging speed of this guy or that guy. We are working on this guy. Okay, so are you with me? So although it can have many different node voltages, but we are considering one specific node voltage. Then after that, we have to find out the route to discharge or charge. In this case, what is the route? This is the route for discharge. Then we can find the intermediate nodes. In order to discharge, we must follow this route, and internally we can find another RC network and another RC network. So in this slide simply means that for discharging of this output node, the tau can be well approximated as, of course, if we don't have any kind of this C1 and C2, what will happen? Actually, we can say that will be, the time constant will be R1 plus R2 plus R3. That is actually the case without C2 and C1. However, it means that the currents are flowing, just neglecting all kinds of contribution from C1 and C2. That cannot happen. Think about this case. If we have only R1 and C1, then what will happen? in order to discharge this C1 first, we have to have certain time constant C1 times R1. And if we have only C2 in this case, for example, let's say that there is no C3, there is no C1, then what will happen? Then we must consider a product like R1 plus R2 times C. Simply speaking, these three lines, 1, 2, 3, each of them is representing a time constant to discharge or charge a single capacitor. And in this approximation, we boldly state that just summing them all, 1, 2, 3, will give us the good approximation for discharging this C3. So roughly speaking, it is like this. In order to discharge our C3, the final capacitances, then first of all, we have to discharge C1 and also discharge C2, and finally we can make a certain discharging for C3. So just to sum them up. Of course, actual analysis is not that simple like this, but anyway, this is a good approximation for this complicated system. Originally, if we have to solve it nearly exactly, then what we have to do is to build a certain equation for this node and then node another node. Let's do it together. For example, if we are working on this node, KCL for our output node can be represented by this way. Time derivative of our output voltage times C3. What is it? This is the capacitance current, N plus N V out minus, let's call it as V2, and V2 divided by R3. What is it? This is the branch current flowing from this output node to our voltage 2 node. So that should be 0. It is for our V out node. Let me just repeat once again. For this V2 node, we must have this one. Time derivative of our V2 voltage multiplied by C2. This is corresponding to branch current corresponding to the capacitor current. And also R2 V2 minus V1. That is corresponding to this branch current. Of course, we must consider another branch current flowing this way. That is given by once again. Okay, so V2 minus V out divided by R3, their sum should be 0. This is another KCL for our V2 node. Of course, it's not the end of the story. We have to build final one for V1 node. So simply speaking, by repeating this kind of job, then you will find one term for dV out over dt and another one, and finally another one over dV1 over dt. By solving three coupled differential equations, eventually you will get the solution of this system. So in general, it becomes quite complicated, but fortunately we can make this kind of approximation. Of course, nobody nobody argued that this one is an exact expression. This is just an approximation. But fortunately or unfortunately, we have already made so many approximations for describing our transistor with R and C. So therefore, another approximation introduced in this point can be well justified. Not that much degrading the quality of our analysis, but at the same time we can greatly increase the efficiency of our analysis. So now you have your homework number 4. So please submit your homework number 4 next Tuesday. This is quite a simple one. Just to do this simple calculation. Here we have R and R. They are the same, and C and C. Here you have just two nodes, one node and two nodes. Of course, this is input voltage, and as a function of time, previously it was just 1 volt, and at t equal to 0, we have made a sudden change of our input voltage from 0 to from 1 to 0. So you can expect that since this is a long time biased to 1 volt, so at the initial part it was 1 volt, also it was 1 volt. Initially the output voltage was 1 volt, and suddenly it becomes 1, so the charge stored in this part will be eventually discharged through this R chain. Okay, that is quite easy, exactly same as before. So exactly the same for our three input NAND case with reduced number of RC chains. So it is quite relevant to our discussion. So if we do that approximation, then what will happen? What will be our tau? Please try to calculate. In order to find out the propagation delay of this point, what we have to do is first calculate the contribution from the intermediate capacitor. So we must calculate R times C, but it's not for this capacitor, our target capacitor, but this is for the capacitor located in between through the path. So we have R times C. And how about our target capacitor? It's just C. However, the serial resistance up to here we have R and R, so we must have 2 times R. So as a result of this approximation, once again this is approximation, we will have 3 times RC. So first of all, please draw your exponential decay with this 3 times IC. What is R and what is C? It's up to you. So please use any kind of reasonable value, then you will have this kind of result. Time and voltage, output voltage, and it starts from 1 volt and it will exponentially decrease. So this is the approximation we have already applied in the previous slide. So the real problem in this homework number 4 is, please draw the exact response of V out. Since you have just 2 unknown variables, you can solve it analytically. So first solve this system analytically and draw that analytic solution here together with this approximation. The goal is just to convince you that our approximation is not that bad. Although our calculation in the analytic solution becomes too complicated, however, more or less the result obtained from our approximation is quite close to the analytic uh, calculation.
그래서 differential equation 두 개 써서 하면 되는 거예요.
Yes, you're right. In this case, you have to use the differential equation. Then please try to find out the transient solution. Of course, if you can work in the frequency domain, then of course you can also use it. Any analytic method is welcome. So please do your own job to get your analytic solution. The solution is just given. However, how can you find it? Depending on your background, you can find many different ways. Okay. So therefore, actually, it means that I'm just saying that this kind of this propagation delay calculation is not accurate. However, from this homework number 4, please understand this, although this is not an exact approach, but it is quite much acceptable approach. So that's the reason why we do this homework number 4. Okay.
이 그림이 이 회로가 나타내는 건 지금 뭐 어떤 인버터나 그런 건 아니죠, 그냥 뭐.
Oh, yes. So this is just a simple RC circuit. However, you can treat it, or you can imagine that when you have, for example, 2-input NAND, then actually that will be your relevant example. For example, let's draw. If you have 2-input NAND gate, let's say this is your input A and your input B, and this is your V out, and this one can be well approximated to this way. R, this R is corresponding to contribution from this one, and this R will be related with this R, and here we have a capacitance originated from the diffusion capacitance between transistor A and B, that is corresponding to this one. And here we have an output capacitance here, which is originated from transistor A and also its PMOS part. Here we have also a pull-up network, and pull-up network also contributed diffusion capacitances, and that is corresponding to this C value.
그럼 V인은 어디에 나옵니까?
So of course in this case Vin is corresponding to our ground.
V인이 1V에서 0으로 이 어그럽트하게 내려가는 순간을 묘사를 하려면 접시는 계속 0V잖아요.
Yes, you're right. Yeah.
이걸 어떻게 묘사를 하나요?
So let me just restate his question once again. So I have made an analogy between this 2-input NAND case and this simple RC circuit. But he asked me a question like, in this NAND case, this part is always grounded, and I'm assuming that the V input is suddenly changed from 1 to 0. So what is it? If we do really make a one-to-one correspondence between this NAND gate and that, then we must have this one here instead of this guy. Let me just draw in a more clear way. So that is quite a good question. So okay, I never thought about that, but that is a good question. So let me just draw one-to-one correspondence. So ground here, and here we have resistor. However, please note that before time equal to 0, the transistor was shut down. Okay. Therefore, although here we have resistance R, but that was disconnected. And this point is corresponding to the shared point between A and B. And here we have once again another R. However, that was also previously disconnected. And here we have capacitance, and also it has capacitance. This is the situation when t equal to or a negative number. So when we were in the previous, before switching, we had this kind of behavior. So after that, when t is larger than 0, then suddenly this due to the change of voltage A and B, now we have connected line and connected line. So that's the reason why this kind of behavior can be well approximated or well described as sudden decrease of voltage. Because previously, since this network was just disconnected, then its value was just biased to VDD, in this case 1 volt. Only after the switching occurs, then now we have some ability to discharge our voltage. It is this behavior is well described by this sudden change. Okay, so are you with me? Okay, it was a really good question. So to me, it was so obvious because I was educated in this way more than 20 years. But that was a really good question. Mhm. And if you have any other question, then please interrupt me. Uh, please interrupt me. And it was a really good question. Then from now on, we will use this kind of approximation everywhere in our lecture. I mean that. So whenever we have a chain of RC circuits, then we will use this approximation. So this approximation or yes, this approximation. So let's go to the RC delay model. It's a nice page. So in this example 4.7, now we have instead of inverter, we have 3 input A, B, C, 3 input NAND. So already we have studied in this circuit in our previous lecture 4.2. Do you remember this diagram? So here, why we have this kind of seemingly not that obvious with values. So these are obtained to give us just worst case resistance of R. Also, these are obtained to give us the effective resistance of R. So everybody remember this, the reason why we have to have this ratio. Of course, once again, we can use it in this way. Then what will happen? If we use this kind of a small N MOSFET, then the immediate result of this one will be the skewness of our voltage transfer curve, because P MOSFET is now much 3 times more stronger than this N MOSFET pull down network. Then our voltage transfer curve will be heavily skewed. So this is not a desirable way. So that's the reason why we have to have introduced this kind of ratio. And after that, here we have 3 P MOSFET. 3 P MOSFET contribute 2C 2C, 2C from its diffusion capacitances, and also this MOSFET contribute 3C for its drain diffusion capacitance. So summing them all, we can have 9C. So that was the situation we have considered. So now we say we have H copies. So you now understand why we are using the alphabet H for this number of copies, because H is reserved for in this course for what? Fan out. So number of load relative to the driver. From the viewpoint of driver, how large the entire load. So since they are the same inverters, so this is the same inverter, this is the same NAND and this is the same NAND, we can just count the number of NAND gates. And for example, if we have NAND, after that, let's say that if we add more inverters here, then if we have, for example, here we can find 1, 2, 3, 4, so H equal to 4 case. However, let's think about this one. Then in this case, is this H equal to 4 or not? So when we just count the number of logic gates, load gates, then we can say H equal to 4. However, it's not. Please note that H is not just count or number of load gates, but it is normalized by the strength of our driver gate. So maybe you can expect that this one is stronger and this one is weaker, so you can expect certain difference from just counter number 4. Okay, anyway, let's come back to our original discussion. We are now considering the inverter whose loads are identical. Also, this is not inverter, this is a NAND gate, and whose loads are also identical H inverters. Oh, sorry, NAND gate. Sorry about that. Sorry. I continuously make mistakes. So in this case, wow, here we have H times of 5 times C. Why we have this one? Because each input A, B, C that has input capacitance of 5 times C, because here we have one from the P MOSFET and one from N MOSFET. So they contribute equally. So we have 5 times C. Okay, then okay. So in this case, now everybody understand this is 5 times HC is the load capacitance of this driver. Yes, this is driver stage, and we have 5 times HC. Then let's try to now calculate the propagation delay. For example, up to now we have always thought about the folding phase, output folding phase. Then let's do that. So how about the overall capacitance connected to the Y point? So this is Y. Output is denoted as Y in this book. Then we can have 5 times 9 plus 5H times C, because they are in parallel. After that, here we have the contribution from this top N MOSFET. It is just given by 1/3 of R. And here we have 3C, and once again 1/3 R and 3C. After that, here we have final RC, and that is grounded. So in this case, what will be the tau? So please note that once again we are talking about the propagation delay of this output node. So we have to find the path this way, and internally we found these two nodes. So simply speaking, we must calculate 3 R over 3 times 3C. What is it? This component is used to charge this lowest one, bottom one. And how about the next one? In order to charge the middle one, 3C, we have to have two serially connected resistors. So R over 3 and R over 3. So that will be the contribution for this middle capacitor. And finally, we have quite a large load cap here, 9 plus 5H. Then we have to have also finally R. Are you with me? So then let me just do it together with you. So first term will give us RC, and second term will give us 2 times RC, and third term will give us 9 plus 5H RC. When sum them all, then we will have 12 times 5H times RC. That will be the expected propagation delay when we consider output falling transition, because we are now talking about this pull down network. So this transition is related with falling transition. Of course, there is no guarantee that this number is also goes for the rising transition. We must draw completely different RC network for this case. So let's just go to this one. So now when we consider this falling transition, we can have it this way. How about the rising transition? In the case of a rising transition, rising means that here we have 3 P MOSFETs here, 1, 2, and 3, and there is our output node Y, and this is the situation we have to consider when we have a rising transition. But you know, in this case we have a transistor A, transistor B, and transistor C. What is the worst case? The worst case is only one of them is turned on, so the weakest transition can happen, or the slowest transition can happen. So what is the best situation? In the best situation, all of transistor A, B, C are working together to charge our load capacitor, shown here 9 times 9 plus 5H times C. Okay, so in this case we are talking about the worst case, so we consider just R. Please note that if we consider the best case, then this number will not be like this. The best case, then we will have a much smaller value over 1/3 of R. Okay, So this is the worst case. Then, wow, now we have already considered the P MOSFET. That's it. So actually not. So please a little bit more careful. Why? In this case, we can have three different cases, like here, here, here. Let's say that we are turned on only A. Yes, A is turned on and B and C are turned off. If we have a configuration like this, C, B, A, then what will happen? Only A is turned on, so now A is turned off, due to the duality. And now B and C, in this case, they are turned on. This is the situation. Are you with me? Of course, if we have different configuration like A, B, C, then what will happen? A is turned off and B, C are turned on. In this case, actually we cannot see any contribution from B and C. However, we are now talking about the worst case, and in the worst case, we have the turned on N MOSFET here, C and B. Then what will happen? In this worst case, now since C is turned on, now we can see the contribution like R over C, R over 3, and here we can see the 3C. And even the transistor B is turned on, so we can see 3 over R over C is turned on, and here we have once again 3C. This is the case. What is this 3C in this diagram? This is the 3C, and this is your B transistor, and this is your C transistor. Okay, so everybody are with me? If we have different case, for example, if C is turned off, then actually this switch will be gone and all kinds of these dependent branches will be disappeared. However, in the worst case, since both of C and B transistors are turned on, so we have to consider the capacitances shown here and shown here. So, so compared with the case like this, for example, if you have this kind of behavior or this kind of configuration, 5 times 9 plus 5 HC, then what will be the tau? The tau will be 9 plus 5 HRC. Your P MOSFET are allowed it just to charge the Y node. However, in this case, when C transistor and B transistors are turned on, your P MOSFET must charge also diffusion cap and diffusion cap of your B transistor or A transistor. Okay, so the time constants will be much longer. Okay. But I wanted to ask you this question. Am I right? So I made a simple question once again. Here you have R, Y, and now you have 9 plus 5 HC. Please concentrate. I just ask you this question. Please calculate tau for this system. And please calculate tau for this system. What is the answer? In this left side, you can immediately understand the answer will be 9.5H times RC. And how about this one? Please try. 9 times C plus, for example, if you are doing in this way, then that's low. And if you are doing something like this, once again, are you with me? If you are doing it this way, there is a misconception. Please note that this VDD is to provide charging current. And what is the final destination? What is your target? Your target is located here. And please consider the path. The path is this one. So, although the case is shown here, in order to charge this Y, only this route is effective route. If you consider the transition time for this node, for example, then obviously you must consider all of these quantities. However, in this approximation, if you are interested with this node, then you should consider only the path between your voltage source and your capacitor. All kinds of this one does not contribute. Then what happens? Of course, even we can understand this case will take longer time. So because it has more dependent capacitances, but this is used to increase the value of this one, or value or voltage of this voltage or that voltage. Please note that. So from this approximation, these two cases gives us the same amount of propagation delay. So are you with me?
어프로시메이션 상태에서는 두 값이 같아요.
Yes, you are right. You are right.
실제로
in reality, so of course there will be a little difference. Yeah. But please note that that is a really good question. My answer is, of course, if you do it exactly, then there will be certain difference. However, that difference is not that high in its first order approximation. In crude sense or log sense, that will give us the same amount of propagation delay. But
즉 하단에 쓰신 그 식은 그러면은 저거 안 쓰는 거죠?
yes, this is a long answer for node Y. But please note that if we are talking about the time to charge this node, then even in this approximation, this expression will be the correct answer. So are you with me? I mean that if we are talking about, so that's the reason why we must understand what is the target node. If the target node is set as this node, then the charging will follow this long path, so all of intermediate capacitances should be charged. However, in this specific example, we are now talking about the target node shown here, so this shortest path only available to our analysis.
실제로 Y를 차징할 때도 밑으로 저희가 세워 나가기 때문에
Yes.
그냥 순수하게 Y만 있는 것보다 더 느리게 차징이 될 것 같아요.
Yes, you are right. So therefore, if we do it really correctly, then we will have different different answers. So in exact sense. However,
그걸 무시해도 될 정도로
yes,
전혀 작게 해준다는 말씀이신가요?
yes, you're right. Then why don't you just do it together with you? So please, you are quite good, good at asking questions. So please, let's do it. Let me a little bit modify our homework problem number 1. I just ask you to draw this one. And what we are talking about right now is how about the behavior at this node. Of course, if we follow our approximation, then what will be the tau? The tau will be, once again, R times C, not 3 times RC. Okay, if we consider this node, the tau will be 3 times RC because we have to consider this product and that product. However, if we consider only this part, that will give us tau equal to RC. So my suggestion is also as a problem number 2, this is worthwhile to assign another problem. No. For problem number 2, please draw the exact solution for this node voltage and also draw your waveform following just tau equal to RC. Then you will find that how much it is good or how much it is bad. Okay? So are you with me? So please check. So that is quite interesting. So all kinds of this confusion comes from our approximation. The system itself is a complicated system, but we just introduced a simple approximation. That's the reason why here we have a little counterintuitive result. For example, this approximation just says that the discharging of this system, the discharging of this node and discharging of this node is identical following our approximation. So are you with me? Because this is RC, it will give us tau equal to RC. And if we concentrate on this node, even in this case, we have just RC as the time constant. So it seems that as he asked me correctly, or another student also asked me correctly, due to the existence of this part, the second IC network, it is certain that there will be certain differences between the behavior of this single IC and this double IC. So let's try to check the exact solution and our approximations. Let's see how worse, how much bad it is. Okay, since you have asked me so good questions, so a little bit the progress is delayed, but I think that it was quite fruitful to all of us. So I will just modify our PowerPoint material to increase the number of problem from 1 to 2. But I think that since problem 2 is just a repetition of problem number 1, that's not that much a burden to you. And do you have any question? Then let's just say that we have done up to here, Then let's try to keep our discussion in next Tuesday. Thank you for your attention.